stuck to the time that was given to you. Thank you very much. Now we have from the UK, Professor David Potts from Geothermal Engineering at the London Imperial College. He has an extraordinary chair, we could say. He is the Joint Director of Civil Engineering and Environmental School of London Imperial College. He's the main developer of the computational platform. Also from the Imperial College, he's designed different geotechnical and geothermal projects in the UK and abroad. He is the author of over 400 scientific publications and also has written handbooks and manuals on geotechnical energy. I'm just going to summarize. He's a member of the Royal Academy of Engineering of the UK. So he's going to talk about the numerical modeling of thermo-active structures as a part of ground source energy systems. Professor Potts, you have the floor.
Thank you for those kind words, and thank you for asking me to come and make this presentation. So I'm going to be talking about thermoactive structures, and I'll define what they are. We've just seen some in the previous presentation. But before I do, some background. I essentially joined Imperial College in 1979, and the two big professors there, Bishop and Skempton, said to me, we need to understand a bit more about this numerical analysis stuff. You've just joined us, you're the guinea pig. So basically, because there was no codes around, I had to start writing a geotechnical finite element program, and I'm still writing it. If I'd have realised 43 years ago that that might be the case, maybe I would have got another job. But anyway, that's where we are. So within the geotechnical group at Imperial, we do field work, we do laboratory experiments, and we do numerical analysis. I'm in the numerical analysis bit. In fact, I've led it for the last 40 years. And we've been developing a computational platform, which has the uninspiring name as the Imperial College Finite Element Program. Let's see if I can get this here. And like all computational codes, I mean, the idea is that we simulate what happens to geotechnical structures. At the kernel, one has got the basic equations, which are equilibrium, mass balance, energy balance. We then basically need to work out how we're actually going to solve them numerically. So there's some approximations. And of course, the thing that causes us a problem is the way soil behaves. It's a three-phase material at best, and it behaves non-linearly in every way it possibly can. So that's at the heart of it. Depending on the equations, we can either do soil dynamics, saturated, unsaturated soils. We need to deal, as you've seen in the previous presentations, tunnels and walls and piles. So we need to do with the structural parts as well as the soil mechanics bit. And importantly, we need to deal with the interface between the two. Now, the program can be applied to lots of things. It's used in research and it's used in industry. I suppose the most prestigious job that it was used on was in looking at the stabilisation measures for the Leaning Tower of Pisa, although that wasn't quite as academically challenging as some of the other projects it's been looking at. But we're going to be looking at thermoactive structures, which is this bit, and these are my colleagues who have been working on this. We've been working on this for about 10 years, and all of these have contributed to this presentation. So what do we mean by geothermal or energy structures? Well, if we look at the geothermal bit, what we're trying to do is to either extract or input energy into the ground. So we're going to use the ground either to take the heat out of it or to put the heat back into it. So basically the ground is a big battery. And we can do this in two ways. We can either have what we call an open loop system, which is not the one I'm going to talk about, but to explain what a closed loop system, let's start with an open loop system, where basically we have some aquifer at depth. We extract, in this particular case, hot water because it's red. We use that hot water to heat the building, which of course cools the water down, and then we pump it back into the aquifer. We often pump it back because if we don't, we actually get surface deformations which affect not only the building that's using it, but all the structures and the services adjacent to it. These are often quite deep, although we do have shallow ones in the UK as well. The alternative is, instead of having something where we extract water and put water back, is that we pump a fluid, usually water with some sort of antifreeze in it. We pump water through a tube, and then it goes through the soil, exchanges heat between the pipe and the soil, and takes it back to the building. And we'll look at that in a bit more detail in a few. And that's closed loop because the water stays in the loop. And we can either do that in boreholes, or we can do it in parts of our structure. So you can see here some tops of some piles, and you can probably see some PVC tubing. There's a single PVC tube loop in some of these piles. But we don't need to put this in just in piles. We can put it in retaining walls. We can put it in the floors, as we've seen earlier, and we can put it in tunnel linings. And the whole objective is that we're using the near surface. And if you look at most cities, most countries, once you get below about 5 meters, the temperature in the ground, if you don't try to extract or input energy into it, is usually constant. So the idea is that in the winter we extract heat from the ground, and in the summer when we're cooling, we put it back in. And the object of the exercise is to optimize it such that there's a net change. Because if there's a net change, then may well have some serious issues, as we'll see later. So this is what we're talking about, these sort of structures. And what I'm going to talk about in a minute is what the heat, taking it out or changing the heat in the ground, actually does to these structures and adjacent structures. So this is an outline of what I'm going to do. I'm going to briefly show an equation, which for civil engineers won't be a problem, but the audience is a bit mixed. But it explains a lot of where the complexities and the uncertainties come from. I'm then just going to show the example of a pile, look at some more piles, a tunnel lining and a retaining wall, to give you a feel for understanding how these things behave and how they affect each other. And this is from the point of view of designing the structures themselves, and how, if you are going to extract heat and put heat into the ground, you could affect adjacent services, adjacent structures, and upset people in the process. So this is what we're looking for. For one of the reasons for looking at it, or the driving force, is that certainly in the UK, people are concerned about, well, if I put this extraction and input into the ground in my structure, am I going to be sued by the bloke next door because his structure started to fall down? Or is London Underground going to come along to me and say, I've jammed its escalator? And this is the uncertainty of what's going on is actually causing a break on using these systems in the urban environment. So I'm going to show this is the only equation. It's a build-up slide. It's basically a matrix equation. It's, as it's shown here, it's the mechanical behaviour of soils, or it could be a structure, where you have a stiffness matrix times some displacements equals some forces. And this is the thing that we're all brought up with as undergraduates when we're analysing structures. It's a finite element matrix. And clearly we need to define the strength parameters of our soil and the stiffness of our soil. And this sort of analysis with just this part is the sort of thing we could use to analyse the short-term behaviour of a wind turbine foundation, and certainly we've used it to look at the monopiles foundation. And just to note, the soil stiffness here is non-linear. It changes with strain. Everything in soil mechanics is non-linear, which is what makes it different to a lot of structural behaviour. So we can deal with short-term and we can deal with long-term if we just deal with the stiffness matrix. If we want to deal with time, for example, and I'm going to show an example in a minute, if we want to say, well, what's going to happen after 6 years, or will my structure fall down before it gets to the long term, we need to advance our analysis and introduce seepage, the way excess pore pressures dissipate that are created when we load the soil initially. So we need to, so this is essentially a storage term and Darcy's law, and of course here is the volume change, which makes this equation equivalent to Terzaghi's one-dimensional equation in one dimension, and of course this gives us the pore pressure. We've now got displacement degrees of freedom, pore pressures degrees of freedom, and flow. And by combining these and adding in the fact that the permeability, and of course permeability is non-linear as well, it's dependent on void ratio, we get a much more difficult set of equations. But it does allow us to analyse another class of problems. And as an example, this is a big pit that was dug at Heathrow Terminal 5. If you go to Heathrow and you're in Terminal 5, 3A flights usually go there, then there's as much under the ground as there is above it. And they dug this big pit because they wanted to build in the pit and then build out of it. But this pit is got to stand up, or had to stand up for 1 or 2 years. And if it had been designed to stand up in the long term, it would have been slopes would have been far too shallow. So we needed to know what the transient behaviour of this slope was going to be. London clay is also strain softening material, so we get progressive failure. And we did the analysis, and the analysis said that to get a deep-seated slope, it was going to occur in about 6 years. They only had it open for about a year and a half, so that was fine. But the analysis showed that we were going to get superficial slides, and exactly what they got during the time it was open. So this is neither short-term or long-term, but adding the complexity to the analysis, and of course to analyse this you must do numerical analysis, allowed us to do so. Now, you can see we went from one submatrix to 4 submatrices. When we add temperature into this, we end up with another set, and we end up with 5 submatrices. This is the conduction term, which is the way that the heat goes through a solid, either the soil or the water. And there's also an advection term. If the water's flowing, heat can actually travel with the water. And this really causes some issues. We've also got the cross-coupling term. So here, basically, the temperature actually affects the equilibrium equation, because the temperature will cause volume expansion. As you heat something up, it expands. Unfortunately, in soil mechanics, the water part expands more than the soil part. So basically, if you heat something up, you'll get pore pressures in it, which reduces your effective stresses, which can actually cause the whole thing to foul, because its strength goes down. And of course, temperature affects both the density and the viscosity of water. So there's lots of cross-coupling in here. And we need these extra parameters to go in here, all of which are essentially non-linear. So to analyse a THM problem, i.e. the thermo-active foundations, we need to actually use this approach. And hopefully by building it up as I've done, you can see that it gets more complex and more uncertain. Uncertain in two ways. We need more parameters which we might not know very much about, and how they vary with temperature and time and space and pressure. But also, when you look at the software that's implemented that you can actually use, you have to make sure they've all got the right equations in, and if they haven't, which equations that they've got, so what they can actually satisfy and what they can't. But let's assume we can do this, and as a profession we can, and we do. So now we can analyse the sort of problem that we've been talking about here, where we've got some sort of the soil. Here I've actually put a pile in here. On this particular case, we're trying to extract heat, so we circulate a fluid through the pipes. It goes in colder. The soil heats it up. It comes out. It goes into our heat pump. The heat pump extracts it and perhaps increases the temperature by compressing it, and it goes through our building, heats our building up, comes back down here and goes through again. Meanwhile, here the cold water, the heat's been taken out of it, it goes back and gets heated up. And the opposite occurs if we are actually in the summer cooling the building down and trying to store the heat, or if we wanted to use some other source of heat and store it in the ground. But these so-called thermo-active structures can either be piles, as here, they can be a wall or they can be a tunnel lining. And their purpose is to exchange. Right, so let's just have a look at a simple problem, just to get a feel for that it's not quite as simple as some people think. I've had conversations with people who use these structures, for example, for a pile, and I say, well, it gets a bit complex. And they turn around and say, no, it's Mickey Mouse. All you need to do is you take the coefficient of expansion of the concrete, which is about 8 times 10 to the minus 6. You multiply it by the pile length, and you multiply it by the temperature change, say 20 times 20, and you get about 3 millimeters of movement of your pile, so it's a non-problem. Well, they're forgetting the fact that you're heating up the soil as well, and you're doing various other things. So it's not a simple problem. And just to show it, here we're going to take a pile which is 23 metres deep. It's got a diameter of 0.55. We're going to look at something else with this pile in a minute. It's in London clay. I come from London. And what we're going to do, we're going to load the pile, because the pile is obviously going to have a load on it. It's a three-headed pile. We're going to load it, so it's got a safety factor in terms of load factor of about 2.5, so it's got 1,200 kilonewtons on the top. And then we're going to apply a cooling cycle to it, which is essentially the winter where we're heating the building, so we're cooling the ground, cooling the pile. So the ambient temperature is 9.5, we cool it by 15 degrees. We hold it, which is an approximation, obviously, how it would actually work in practice. And then the summer comes and we want to cool the building, so therefore we're going to heat up the ground. Now, if we actually, this is depth down the pile, this is 23 metres long, this pile, and this is the vertical displacement of the pile, and this is just due to putting the load on. So no temperature change, it's in the ambient temperature. You can see that, as you'd expect, the pile head compresses, by this case by 2 millimetres. Settlement is negative. And the axial stress in the pile, if you like, the load in the pile, it is expressed as the load 1,200 divided by the area, is an axial stress of about 5,000, and that decays with depth. There's very little end bearing on this pile, it's all taken in friction. It's in London clay. And this is what happens if we just load it up. If we then apply, this is decided to go and strut. So if we now change the temperature on this pile, the pile will try to shrink. But the soil at the side of it is not going to shrink as much. So the support that the soil is giving to the side of the pile, which is how you transfer the load from the building via the pile to the soil, is actually going to change. And you can see two things happen because of this. One, the pile head comes down. In fact, it comes down by as much as it did when it was loaded. And there's going to be a change in the axial stress in the pile due to the fact that the skin friction's changed because the relative movement between the pile and the soil has changed because the soil is not shrinking as much as the pile. And you can see here, in this particular case, we get tension in the bottom of the pile. So the bottom of the pile will actually pull apart if there's no reinforcing in there. So this is not Mickey Mouse. This is problematic. And then if we leave it there, so the first one, this one, was at this point. If we leave it there, then what happens is the cooling will dissipate into the soil and the soil will start to expand. That will change the skin friction on the side of the pile. We get more movement, but we get a slight relaxation or a change in the stress in the sense that it's coming back to the distribution it had before we started. And then if we actually now heat it, so we go to here in our cycle, we can see now our pile moves the other way, it tries to expand, and we see another change in the skin friction on the side and the axial forces in the pile. And these changes are substantial. So one needs to take account of it when one's designing the pile. And this is occurring because of the difference in the coefficients of expansion and in the fact that there is pore pressures being generated in the soil by the heating and the cooling. And if we actually go to the end of the heating, we get a slight relaxation. If we go to here, when we've actually taken the load off, we end up with the grey one. So basically, even though we've done this cycle and ended back where we started with, our pile is not in the same position and the load distribution in the pile has changed. And of course, we will then take this on to the next year, the next year, and the next year. So we need to account for this. So just going back, keeping with this single pile actually was a result of an experiment that was done in a field test that was done in the UK, where they actually took a pile of these dimensions, they loaded it to a mechanical load of 1200, which is a load factor of safety of 2.5, and then they applied the temperatures. But they instrumented the pile, they put optic fibres in to measure the strains in the pile, and they put vibrating wire strain gauges to measure the strains also in the pile. So these things are measuring the same thing, or ideally they're measuring the same thing. This is the load. So this is before they change the temperature in the fluid. This is the vibrating wire strain gauges, and this is the fibre optic measurements. And you can see they quite agree. And this is the numerical prediction of the load distribution, or sorry, the axial strain distribution in the pile, which actually looks like that axial stress distribution. I'm getting orders from the back that I'm moving around. Should put some things on the floor so I don't move. Now, this is what they actually applied to the tubes. This is what happens at the end of cooling. There is some disagreement between our measurements, which is probably due to the temperature effect not being properly dealt with in our instrumentation. But you can see that it's not too bad, and then the numerical analysis, there's a change. The numerical analysis is agreeing. and this is what happens if you heat it. There's better agreement now. So this is at this point. I mean, this was a real thing, so there was all sorts of issues with the heating breaking down and one thing and another when they started to heat the fluid. But you can see that the numerical analysis is not producing silly results. It actually agrees with what happens in reality, so we can have some confidence that we might be getting something realistic out of it. Now, the sad thing about a single pile with a load on it is that the load on the top of the pile can't change. All you're doing is getting movements and a redistribution of stress. So let's look at something that's a bit more realistic. And let's take a pile group, 16 piles, 4 by 4, symmetrically placed, with a pile cap. Pile cap is 1 metre thick. Piles are 0.9 of a diameter. Now, if we were designing this pile group and all the piles had the same length, then the perimeter piles, the ones around the outside, would actually take a bigger load than the ones in the middle. We all know that. So often, when we're designing a pile group, we will actually make the outside piles actually not so long, so they actually, and in this case, 4 metres not so long, so that the piles tend to take the same load. And the reason for that is that reduces the bending moments in the raft and equalises the load. So we've done both cases, but I'm taking this case now. So if you look at here, we've got the mechanical axial force. Now this is actually kilonewtons in the pile with depth. This is the central pile. This is just due to the putting the load on the pile, which has got a factor of safety of about 2.5. We maintain that constant load, but this is the distribution of the load in the central piles, in these ones. These 4 are all symmetric, so they're the same. And then we've got the perimeter pile, and you see by adjusting the outside piles to be 4 metres short, we've got something that looks that they've got the same load in. You can't necessarily get it totally right. You'd have to be 3.67 or something theoretically to get the same load in the pile. But they've got about the same load in the pile. So now we apply the temperature change. So we're going to cool it. So we go from the red lines to the blue lines. But we're only going to make the outside piles thermally active. The reason being, it's pretty pointless making these thermally active because they're going to be swamped by the effect of the ones round them. So we could do, and you could make just the corner ones, and we've done that as well. But basically, in this particular case, something that's realistic, we actually have taken the outside ones. Now, because we're cooling it, the peripheral ones are going to try to shrink. So the axial load in those actually goes down, which is what you'd expect. But the load on the raft is the same, so something has to take the load. So the central piles actually get an increase in load, even though they will be being cooled by the outside ones. And this load is a substantial part of the original load. So if you designed your reinforcing in your pile for this load, you might want to think about, well, maybe that's not the maximum load I should have designed it for. Plus, now you've got different loads in the central ones to the external ones, which is giving you bending moments in your raft, which you designed before such that you didn't have it. And then when we allow the temperatures to stay there for the 6 months, we get the soil now cooling down as well as just the piles, and we get a relaxation back to the initial values of the axial force in the pile. And then we heat it, we go to here, and of course these outside ones now want to expand, and therefore they increase their load, and the inside ones here now, even though there's heating up going in the soil, they're actually having a reduction in load. And again, if we allow for this heat to sit there for a time, it's a transient problem, we still get changes and we get this relaxation back to perhaps where they were to start with. But at the end of the cycle here, we have got a difference now in the loads in the past. So we've changed the load distribution by a cycle of heating and cooling. Let's look at perhaps a tunnel lining problem. And here, the history goes that when they built the Crossrail, the latest, it's called the Elizabeth line now. You may have heard on the news, it's now actually 3 years late, £4 billion over budget, but it actually now gets a train from one end to the other end, and that happened first time on Monday, which was yesterday. But it's working. But during its construction, it went across Hyde Park. Imperial College is just down here. This is just around the corner. And we instrumented it when they actually built it. It's not thermo-active. This is just a cross-section showing where we've got a westbound and an eastbound tunnel. And basically, when we did the original hydromechanical coupling, so no temperature, the westbound tunnel was constructed first. 10 months later, the eastbound tunnel. The tunnel linings were assumed to be impermeable. London clay now has got lots of different layers in it. The more we understand it, the more we realise it's much more complex than perhaps we thought 20 years ago. And when we analysed this numerically using a hydromechanical bit, 4 submatrices in the top, we produced the ground movements that they actually got. And this is all published. So what we did was we took this scenario and we said, well, what happens if we take one of these tunnels and we just cool it? We're basically extracting heat from it. And we basically extracted 15 degrees and we extracted it over a month, and then in this particular case we just maintained it. We didn't heat it or cycle it, but we just wanted to see what it would do to the ground surface, because that's an important thing when you're building and analysing tunnels, and what this one might do to this one, or what it might do to itself. And you can see in this diagram here, after a month, you can see this is contours of the temperature, in blue because it's getting colder, and you can see with time the soil is beginning to cool around the tunnel, and that cooling zone gets bigger and bigger, and it's going to be affecting more soil. But if we actually look at the surface settlements, the red line is the measured and predicted, in a way, surface settlement that's just due to construction. So we've got 5 millimetres, 5 millimetres of movement. If we then look at the added movement after 1 month, it is this. So this is not the total, it's what happens just to cooling. And after 6 months, we've got the dotted line, and then a year, and then so on. So if we was to say realistically we would be cooling this tunnel for 6 months and then we might be heating it, you can see that we got 4 millimetres of movement. So the surface movements caused by using this tunnel as a thermoactive structure are relatively substantial when you compare to what happened due to construction. And what's interesting, if we look at the westbound tunnel and we look at the movements, the convergence, in tunneling you often look at the horizontal convergence, which is the change in horizontal diameter and the change in vertical diameter. These are the numbers that we get. So this is the vertical one, and this is the horizontal one. 2 interesting points. One is it happens very quickly. We don't even need 6 months before we get the maximum amount. We get this shape, exaggerated, but these numbers are very small, a couple of millimetres. This is not really going to be a big problem with a new tunnel. It may well be a problem if this was an escalator tunnel, for London Underground, but then they probably wouldn't put cooling in it. If we then look at the eastbound tunnel and superimpose it, the eastbound tunnel, the movements are less, but they're still substantial. And yet, the cooling front hasn't reached it. This is cooling, the soil is shrinking, it's causing this shape to the tunnel over here. And we find this if we have a piled foundation and a tunnel next to it. You do not need the heating front to get to the tunnel before the tunnel is actually reacting to the heating front. And this is because of the expansion, contraction of the soil and the change in pore pressures. So now we get this shape where the cross-section area is much the same, whereas it's shrunk here because of the cooling. But again, if we, just to point out, these are the pore pressures that are being caused by this difference in the expansion of water and the expansion of the soil particles. And you can see that there's areas of where we're getting these negative pore pressures because we're cooling it, so therefore the water's trying to shrink more than the soil. It's not very permeable, it's London clay, so the water can't dissipate, so we get these negative pore pressures. And they're not symmetrical around the tunnel, and this is because it's a complex boundary value problem, and gravity is affecting the water flow and all the rest of it. And we do get changes in stresses in the lining. It's here, this is the thrust in the lining. This point is 0, and then we've gone round the tunnel, and we do get changes. We get a big change originally after a month, and then we get relaxation. But these changes are minimal compared to the actual thrust in that lining due to construction. So this lining is not really being very affected by the fact that we've actually this is the westbound. Even though we're cooling it, it's not really being affected to a great degree, not like the park. And just last example is if taking a retaining wall, where we're not looking at the heating, cooling in the retaining wall. We're looking at what happens when we do something at the side of it. So we've taken a London a London scenario, which was actually originally monitored years ago. It didn't have this there. This is we're inventing this. So we're taking a typical basement in London, and then we're going to apply temperature change to two scenarios that might be occurred. One, we're going to use boreholes here, which are 67 metres deep, so they go right down here, as we see in the next slide. Alternatively, we're going to use piles with tubes in, and we're going to look at what this does to the problem. This is when we're heating it up. You can see the obvious thing, the boreholes are causing a much bigger area. There's a much smaller area of temperature, although the temperature is a lot bigger within the thermally active piles. Interesting thing is, even though this temperature has changed by 15 degrees here and 15 degrees on the sides of these, or in these boreholes, there's very little change on the wall in terms of temperature. So the wall is not really being affected by the temperature. If we look at the movements of the ground surface, which of course we'd be interested in for the two, if we're expanding, if we're thermally injecting into the soil, we cause quite large movements for the borehole case, less movements for the THP case, but still substantial movements of the ground, which could affect any building or services that are there. And then when we cool it, it comes down, so we get quite large cyclic variation in what's happening to the ground. And if we look at the behaviour of the wall, although the temperature wasn't changing in the wall is moving. When we heat these things up, it pushes the wall into the excavation, even though there's a base slab there, of 4 millimetres, 5, 6 millimetres for the borehole and 3 for the thing. And we get get bending moment changes in the wall. These are changes just due to heating up the ground. And these are movements just due to heating up the ground. And when we cool it, it goes back the other way. And when you compare these movements and these bending moments, 200, these, with the ones that were in the wall, so the wall would be designed for these, they are significant. So, just to summarise, the thermal effects, when you're doing this, are important to the design, or can be important to the design. And it's not just the structure that's got the tubes in it, or is actually active, it's what it does to the rest of the structures that are around it. Some of these forces and movements can be significant, and then they need to be dealt with. It's a transient problem. That's why you need this advanced numerical analysis. But because we have the ability to analyse it, you can actually tune these structures and get round the problem. So we feel, and I think consultants and contractors feel, that by having the tools, we can now get rid of this problem that they were having about should we do this or shouldn't we do this? Are we going to upset the bloke next door because his wall started to crack, the rest of it. But one thing we do need, and it's a plea to all of those people that are putting these things in the ground, is we need instrumented cases. And please, when you instrument, can you make sure the instruments are not going to be adversely affected by the temperature change? Because as you saw with the vibrating strain gauges and the optic fibres, they don't necessarily give similar results, which they should. And the last slide is, if anyone's interested, all of this stuff is in these publications. Thank you. Thank you.